Hi, everybody. Thanks for coming out, and thanks for finding my talk. I'm sorry that it wasn't announced very early. I was a bit of a late entry to get this talk into the re:Invent schedule. So I'm going to go through a whole bunch of things today, and really got 5 different topics that I'm going to sort of segue through. First, talking about disruption and the opportunities that brings. And then the evolution of microservices, how we've gone kind of from monoliths through microservices into serverless. The cloud-native architectures, what those look like, how do we think about the principles of cloud-native. And then talk about dependency management, also known as lock-in, but I think dependency management is the right term to use nowadays. And at the end, I'll talk about chaos architecture. I think this is a topic you're going to hear more and more about, particularly through into next year. It's starting to bubble up as an interesting topic. So that's what I'll cover. So let's get going and talk about the transformation. So in the old world, we had companies that you have employees sitting at desks with fixed workstations. There's factories, there's supply chain, you get updates that come in on bits of paper that get entered. You have sales channels where you put things in boxes and they get shipped to people. And your marketing analytics was based off of traditional media, TV, print adverts. You're trying to figure out if anyone saw your ad on TV. It's hard work to do that. So that's the old world. Basically, the IT scaled with the number of employees you had, or the number of factories you had, or the number of sales channels you had. And that's the scope of IT in the old world. So in the new world, it got a bit more interesting. So employees are now mobile, they're fully connected, you're building applications for them, they have all kinds of productivity aids that are actually engaging in what they're doing. Your factories and supply chain are doing continuous supply tracking, just-in-time production. You've got everything instrumented, very much more detail. You have online sales and delivery. Your things you're making, you don't put them in a box and ship them. They are internet connected, IoT. They are reporting back to you all the time. And marketing's gone online. So you're tracking social media. If somebody says something bad about you on Twitter, you want to have a tool that will respond and engage with them and do those kinds of things. So this is the new world, and IT in this world scales with the number of things you've made, or the number of customers you have, or the number of people talking about you. And that is a radically different scale and a whole lot of new challenges. So that's why I think there's been this sort of this is kind of generally referred to as digital disruption. This is the fact that the internet has connected enterprises to their customers is actually what's caused that interruption, that disruption. So the new kinds of things that you need to build. You need to build personalization, because now you can know who is watching TV. And this is one of the really differentiating things for companies like Netflix. They can see, I know exactly who's watching TV, when they're watching it, rather than sort of asking some company like Nielsen who they think probably watched that show at 9 p.m. on a Tuesday. They know exactly who watched it, and then they can optimize for what you want to watch next. So the whole thing is built around customer tracking. You can build all these systems for that, and you have all these new channels that go direct to customer. That's a whole load of new things that everyone's learning to build. So I'm going to talk a bit about the way this has evolved as we go through, and I'm going to start by looking at kind of the business logic. So in the past, we have monoliths, and then we got into microservices, and now we're playing around with functions. So why did that happen? Start by looking at the original monolith. So about a decade ago, this was current state of the art. You built your monolithic application. If you tried to split it into chunks, you found that you could only make the chunks so small before it got too slow. And that's because we were passing these big fat chunks of XML back and forth. We were doing SOAP calls. People remember SOAP and XML, right? That was a pretty slow way of doing things. We had 1 gigabit networks, and you could only pass things around so many times before you'd burn up your latency budget. Right. So if we sort of fast forward about 5 years, we'd gone to 10 gigabit networks. We were using JSON and binary encodings, REST calls. We got away from all the SOAP stuff. And we're running orders of magnitude faster interactions. And this really let us break our application into the chunks that we wanted. So the problem with the first time around SOA was that we weren't actually able to get the services down to the right size. And what really enabled the microservices revolution was that we have the efficiency to be able to do a fair amount of work, even though, when you hit your home page, this is the services that are, returning just that home page, or that single request is going through an awful lot of work. And the fact it's inefficient, but it lets you optimize for something else, because we have enough efficiency in the underlying infrastructure that we're able to iterate and get our development timescales to speed up a lot. So the real benefit here is you're able to innovate independently and deploy independently and upgrade everything. But if we took that monolith and we broke it into microservices, a lot of the pieces of that monolith turned into individual services. And many of those services turned into very common things. Like I have some kind of storage part in my monolith that became a storage service. I had some kind of queuing system that turned into a service. So the next phase was we started to recognize that out of all of those microservices we'd built, a lot of them were just off-the-shelf standard things. So we started to replace them with SQS and DynamoDB, SNS, things like that. And what was left, the services we actually had to write, are the ones in the middle. This is the business logic, it's the glue between the bricks. And sort of my best analogy for think about AWS is it's now like 100 different shapes of Lego brick, and we give you the plans to assemble it into whatever you want. So think of the Lambda functions as sort of super glue to glue together your bricks. And what we're able to do is break up these functions into into individual functions. So the services start to break apart. And then the other thing that was interesting was it all became completely ephemeral. So I've got this whole thing grayed out because it's not doing any work. And when a request comes in, it wakes up some Lambda functions, wakes up that service, and in between, it's really not doing anything. This is kind of a very simplified view of what happens in a serverless sort of environment. But the point here is that when it's idle, it shuts down. It's not doing any work. It costs nothing to run. So there's two things about the whole serverless evolution here. One is that the cost of running it is very low, particularly if you have spiky workloads or you want to scale down to zero at certain times. All right. Particularly if you're a startup, we're seeing a bunch of startups serverless first because they don't have customers yet, but they can build out all their functionality. And if somebody ever uses it, the capacity is there on demand. So that kind of capability is excellent for startups. It's excellent for prototypes. And we're seeing lots of enterprises use it for internal IT apps that have very spiky workloads. Nobody's using them at the weekend, all those kinds of things. So that's one aspect, the low cost to run. The other one is they're extremely fast to develop because I'm only having to write the glue. The other service is already up and running. I don't have to spend forever trying to figure out how to install and run Kafka. I have Kinesis. I don't have to figure out how to install and run a database. I just use DynamoDB. It's already there. It works at scale. It's reliable. There's just much less work. And I've got lots of examples of customers taking projects that were taking months doing it the other way, doing it in days with serverless. It's not just a few percent faster. It's orders of magnitude faster. And I think that these two reasons are the key thing that why serverless is very interesting right now. Quick to build and low cost to run. So that's really what I'm seeing as business logic evolves nowadays. There we go. All right. So that's the business logic piece. So let's have a look at what happens to the storage tier. We're having to denormalize it a bit. We started with these monolithic databases, and then there's this kind of thing. We used to call the schema the kitchen sink schema. If any of you have had like a relational database that you've modified every few weeks for years on end, which it turns into this monstrous thing that you can't modify anymore. So we used to call them kitchen sinks. So I'll do a little analogy there. But we're trying to get to a denormalized model because if you have a lot of microservices and you have to deploy them all at once because you've got to do that alter table to your database as part of the deploy, you've actually built a distributed monolith. And you've got all the disadvantages of both. You're not really getting the ability to do independent deploys. So let's look at this a little bit more. These monolithic databases, they're kind of expensive, they're hard to create and run, and you want to get to something that's a bit easier to deal with. The problem is your schema is sitting there, and then it got more complicated, and then it's got all kinds of business logic lurking in PL SQL and things sort of hiding in the bottom of your system. And back about 10 years ago, or when I was working on the sort of Netflix transition, untangling this was actually the hardest part of our transition. All of the other different pieces were interesting transitions, but untangling the database was I think, the thing that the developers found hardest to work with. So I'm going to do an analogy using this kitchen sink model. And I'd like to point out at this point, I do not write my own slides anymore. I have this company, and I said, please draw pictures of kitchen sink, and just send them sketches, and they do these wonderful slides for me. It's one of the best parts about this new job at Amazon. I have a budget to make people make my slides look cool. So think of this as the kitchen sink in kind of a student accommodation where everything's kind of piled in there and it's full dirty stuff and broken glass, and you don't want to have to touch it. It's not very sanitary. You've got flies and things around it. So what you really want to do is untangle this thing. So we're going to kind of pull out the spoons, and we're going to pull out the knives, and we're going to pull out the plates and the glasses and do all this kind of stuff. Okay, so that's a lot cleaner. Right, but there's a problem here. So let's go and have a look. How many complete sets? Turns out we're missing a spoon. Right, so this is the problem with having a denormalized database model, that you don't have the consistency, you have to keep track of it, and you have to build at least a mechanism in your system for keeping all these databases in sync. Now, if you've ever been at any decent-sized company, you've got more than one database already, you already have this problem, you're already trying to keep databases in sync. But when you denormalize, you probably have an order of magnitude more databases. Instead of 3 or 4 databases, you have 30 or 40, something like that. So you have to pay more attention to when you do a write, how does that write sprinkle across all the databases, and how does it make sure everything stays up to date? All right. So the trick here is how do you get there? So the main thing, if we're going to add a new use case, so you're going to throw something in the sink, or you're going to create a new place for it. Let's say we want to have a Japanese meal, so we're going to put a sake set and some bowls and things in there. We're going to create a new place to put them rather than lumping them in. And the problem normally is because databases were so hard to create, and you had to go beg to the DBA gods to even get a new table. Getting a whole new database was completely out of question. You just okay, just give me a new table. But now it's trivial to add a new database. It's an API call, and you will just have, RDS will make a new database, or DynamoD will make a new table for you. And we have the database migration service, which will actually keep these things in sync. We are now over 40,000 databases have been migrated with DMS. It'll take Oracle and move it to Postgres. It'll move SQL Server to MySQL. It'll do a bunch of different translations, and it's a bidirectional copy. So it'll actually keep both of them in sync, because these translations never you don't just shut it down at a weekend and move it over. You usually have to run side by side for a while. So we're seeing a lot of these migrations, particularly to the open source database standards around Postgres and MySQL. All right, so that's basically it. And if you just go around picking things off, this sort of the strangler pattern for databases, you pick off a materialized view and put it in a database, or some table and put it in a database. And you pick it until what's left in the center is actually a set of simpler systems. Some of them might be NoSQL systems, really just one index table. Others might actually be a relational database, but it's a single function relational database that just does one thing. It's not this kitchen sink of every use case you had bundled into one big place. So I think this is another important part of the whole microservices transition. And as I say, this is actually one of the hardest part that we ran into when we were trying to retrain all of our developers to think in this new way, because you can't do transactions anymore and you can't do joins anymore because your data isn't in one database. It's a distributed transaction and join problem that you have to work for. All right, so let's talk a bit about cloud native architecture. If you think about how people move to cloud, the first reason they move is typically for speed, right? If I can get a machine in a minute instead of a month, that sounds good. I can deploy my application really quickly. But then you just end up with the same junk you were piling up in the data center, but piling up in the cloud. And it's all very inefficiently run, and you don't really have the management and control around it. You're still running it as if it was in the data center. You just got your machines more quickly. So I call that data center native architecture, right? So you have you keep forklifting more machines into your data center, and it sits there and it lives for years, right? It's full of spiders and cobwebs and things like that. But what you really wanted to do was, park it up in the cloud. So that's one approach. But what you're doing in the data center is paying up front, depreciating over 3 years, but in the cloud, you're paying a month after, and you're now paying for the number of seconds you used. Hopefully you noticed a few months ago, we went from hourly billing to billing by the second, after the first minute to get you going. So now we have really fine-grained billing, and you pay a month later. So you don't need to pre-provision capacity because you can get it when you need it, and you don't need to have extra capacity sitting there, just in case something happens in the next few years. So here's the first principle. I'm going to go through a few of these principles. You want to pay for what you used last month, not what you guess you might need next year, right? Okay, let's think about something else. If we're trying to get this done, the way we used to do this is file tickets and wait for people to come back from their coffee breaks and get stuff done. In the cloud, what we really want is self-service, on-demand, no delays. And this is one of the primary characteristics, on-demand, self-service, API-driven. That's when it's a cloud-native application, when you're doing deploys this way. Because when you're deploying and somebody is on lunch break or whatever, you're waiting, right? And you can just keep making those requests. So we're going to deploy by making an API call, self-service, have things happen within minutes, and have that for all of your operational infrastructure moves to that. If you're trying to measure your progress towards cloud native from an old model, one way to do it is to count for every release you do, how many meetings were there and how many tickets were filed. It's maybe like 5 meetings and 40 tickets or whatever. Maybe it's less than that, but it's some number. Publish that as a metric, right? And then basically say, this is bad, make it go down, and see if you can come up with a way to avoid that meeting or remove that ticket. Because the state of the art here is one ticket, and it's a tracking ticket. It's a ticket that auto updates as the thing you're doing progresses through the test pipeline or into automatic deployment. Right? You want to know, you want somewhere to authoritatively record that you made a change to production, and that should be that ticket with the history of all the changes. But it's tooling that is appending to these tickets, and it's all automated. So it goes through some canary pipeline kind of thing. Okay, so if you're trying to deploy stuff, particularly if you're trying to deploy stuff globally, it takes a little while if you decide, I need to launch something in Europe. I don't have any people in Europe, or I don't have any people on the other side of the country. I need to go build a data center there. I've got to hire some people, got to build it out. It takes a long time. But on the cloud, we currently have 16 regions and 117 POPs, which are now programmable thanks to the Lambda at the edge that we announced last week. You can deploy code in 133. Yeah, something like that. You can do mental math on stage. All right, so there's a huge number of places you can deploy code without, and it's just a different drop down on the menu to decide I want to put code there. You don't have to think I have to go hire people and put up buildings and think about where I need and how much capacity I need. And that is another one of these principles, because instant globally distributed applications are the default. That's just a capability that's right there that is much harder to do, and you don't think about that if you're just thinking, I have one place I'm deploying it in my data center. You're not really thinking about what's the implications of deploying this globally. If we look at the way we do regions and zones, let's look at a data center architecture. We have New York, and we have a backup data center in Chicago, and on the cloud architecture, we'd typically use 3 zones, say in Virginia, and 3 zones in Ohio would be kind of our equivalent. And a very topical thing this year, let's have a hurricane. There we go. Oh dear, we flooded the New York data center. So we fell over to Chicago. So that's a fairly typical scenario. And if you want to migrate that kind of scenario to cloud, if you just do a data center kind of obvious migration, you take whatever instances you had, let's say it's a MySQL primary and slave, you already got the config, it's already running on a machine, it may be running in on VMware in a VM, and you want to just migrate that over. The most obvious thing to do is just move it over, but then it's only running in one of the zones in the region. And what you really want to do is something more like a cloud-native migration, where instead of doing that, you migrate over to a service like Aurora, which automatically distributes all your data across 3 zones. There's 6 copies of the data with Aurora. It puts 2 copies in each zone, so you can lose a zone, and you can lose a node, and you still have a resilient, redundant copy, and then there's more scalability in there as well. So that gives you the ability to distribute, and you've got have close to, I mean, the primary, secondary failover between 2 data centers, if you've got a lot of geographic distance there, then it's very asynchronous. But what we're doing between zones within a region is synchronous replication. So they are close enough together. They're typically between 10 kilometers and 100 kilometers apart. Right? You don't go any closer than that, because then the same hurricane or fire or whatever might hit a building. You want them far, but you don't want them any further apart than that, because then the latency would be too high to do the synchronous replication. So that's the philosophy behind the way we do zones and regions. And if you have a hurricane comes by, it's not really going to take out a whole region. It's just going to maybe take out 1 data center if we get really unlucky. And we try not to put data centers in flood zones. I'm like, I've been to like the Jersey Shore, New Jersey area. It's like, there's data centers here? All right. Anyway, talked to one customer and said, yeah, our basement flooded and we moved it. So this is the principle. You want to distribute over zones within a region by default. So let's look at another thing. Elasticity. Data center, it's pretty hard. If you're doing well, if you can get your data center to be consistently over 10% busy. But you still need extra capacity, because spikes will come in and traffic will, quite often you run out of capacity as well as being underutilized. You get both, you're bad on both sides. With the cloud, I think you should be targeting over 40% utilization. And so that's like a 4-to-1 ratio, maybe more than that. If you're doing a really good job, you should be running on a vastly higher multiple ratio. So this takes care of a lot of the cost scenarios, because if you basically are running on 5,000 machines in the data center, you should be able to run on an average of 1,000 machines in the cloud if you're doing a really good job of turning stuff off and being elastic with it. Right? That's kind of a 5-to-1 ratio, something like that. So there's thousands of machines down to that, you want your average, but you may have your peak number of machines in the cloud could be 10,000 machines for a short period of time. Then it could go down to 500 machines. But right, you've got a much more flexible approach. But again, this is one of the harder things to do, because in the data center, you never optimize for turning machines off. And it's very rare to have autoscalers running in a data center environment. It's typically a fixed deployment. So you have to re-architect your apps to be scalable, but there's a huge cost benefit for anything that's running at any large scale. So the way I think about this is, if you've got a fairly large workload with a relatively low rate of change of capacity, autoscalers are great for tracking that. It goes up and down on a daily cycle. Those are the kinds of things that autoscalers are great at. If you've got spiky workloads that go completely idle, then you want to use serverless. And there's some crossover point where you can obviously do anything with either one, but the most efficient thing will be to use serverless at the low end. And as you get to very heavy workloads where you're keeping your Lambda functions totally busy all the time, it may be more effective to have some containers running that as a continuously running workload. But yeah, it's up to you, and there's different trade-offs there. So here's another principle. You want to turn it off when it's idle, because you can get much higher utilization, huge cost savings, and it avoids capacity overflows. Okay, delivery pipeline. Developers building software, you really want to automatically run this through a CI pipeline, build the system, put it into canary testing. The canary should reject some of your things as saying, no, this doesn't really work. And then that passes on into a versioned delivery model. So you want to have blue-green versions, maybe a few old versions lying around, and have the automation to automatically sequence between this. So this is kind of the cloud-native version of the delivery pipeline. And what we're doing here is we're building immutable code. We're doing automated builds. We're generating ephemeral instances, containers, and functions So the blue-green deployments, and then the services themselves and the routing between them should be versioned. If you have to have, if you can only support one version of a service at a time, and you do like a quick replacement and hope the thing doesn't break while you're changing it, you can get away with that for some of the time, but I think that causes a whole lot of problems in your ability to run at speed. You want to be able to support multiple versions, so you can always introduce something new, and you can retire it whenever no one's talking to it anymore. So you end up with a little more versions of things. It's maybe a little complex to visualize, but it's much more resilient, and you can keep your mainstream traffic on really, really well understood, very stable versions of your code, and have lots of experimental versions for A/B tests and experimental traffic and things like that. So here's the set of principles, just to run through them again. If you're following all these, I think you've got a good basis for being cloud native. You want to be pay-as-you-go, self-service, globally distributed, use cross-zone and region availability, have really high utilization, and immutable code deployments. Okay? And I think these principles, they really remain constant. Even though the practices evolve, the technologies evolve, I think these are kind of common principles that you can look at for over a long period of time. All right. So, having gone through all that, let's look at the how do we build on cloud a little bit. What are the opportunities? I'm going to go through a few different areas here. What do I mean by opportunities? So think about startups. If you're a startup in this space, the enterprises are all struggling with their transitions, but the startups are trying to figure out, okay, which enterprise itch can I scratch, right? Where can I find some way to sell something to an enterprise, or how can I support some developers? And if you think about startups, they fall into a number of different categories. You can think of being incremental, right? There's just a better version of the previous thing. And there's a number of areas like that. If you look at monitoring tools, say APM tools, there was, remember the Wiley product from about 10, 15 years ago, was some of that team left and formed AppDynamics, and then that became kind of a new generation, did roughly the same thing, but did it better, had a bit more scalability. And then AppDynamics has gone public now, and there are some ex-AppDynamics people building Instano, which is like another generation of this. And it's just a better version of the thing. And you're just going to, maybe someone will come along with a better version of that at some point in the future. So it's pretty clear there's a need, but you're able to build a faster, better, more scalable version of something people already have. So there's a clear market there, but you're just building a better one. Gap fillers are an interesting one, because if you look at a product line and you say, well, there's an obvious gap here, the problem you have is you have to be able to fill that gap really quickly because everyone else can see the gap. Right? I mean, Docker came out, everyone said, oh, we're going to do Docker for enterprise. It's like lots and lots of people in Docker, but I think Docker's probably going to do Docker for enterprise. Yes, they did actually do a product called Docker for enterprise, but before that product came out, there were lots of startups saying, we're going to do the enterprise version of Docker. And you had to get to market very, very quickly. And this happens also if you look at all the services AWS is doing, you're looking, oh, there's a gap. AWS doesn't do this thing yet. If it's a pretty adjacent gap, you're pretty sure we've noticed the gap too. We're likely to put something in it. So you better be really fast to market if you're going to kind of try to compete with a cloud provider and try and gap fill on them. That doesn't mean you shouldn't do it, because I've seen some startups use their kind of like a trampoline, kind of like get you started. Like you get in here, you get built, you get known, and then you're ready to pivot out of it when that piece of the market, when the gap closes. But you've built a little momentum, and you've established yourself, you built a team, and then you go build the thing you really wanted to build. So it's a valid strategy, but it's a different strategy than, you can't assume that you're going to own that gap. Leverage is another interesting one. AWS is a huge leverage. Our advertising slogan right now is build on, right? Building on top of these things. We are building incredible things that you can build on top of, and particularly for startups, we've enabled a huge set of possibilities. Getting sort of GPU-enabled monstrous machines with, 70 or 100 teraflops of capacity by the minute or by the second, that's an amazing capability. Machines with 4 terabytes of RAM, and next year going to 8 and 16 terabytes of RAM. We've sort of pre-announced that. What can you do with 16 terabytes of RAM? if you work in an enterprise, try going to your ops team and say, I'd like to play with a machine with 4 terabytes of RAM for a few hours. So it's not going to be a happy outcome. Just fire up an X1 on AWS. And the hardest type of startup is a category creator. This is the one where no one understands what you're doing. They can't figure out who would buy that. But you create a new category and you become the brand in that category. Like people talk about the Netflix of thing or the Uber of thing or the Docker of thing because they kind of came in and managed to create a category around themselves. They are the long shots that most attempts fail. But if you manage to get there, you've actually discovered a new gap in the market, and then other people will copy you. You can tell you're a category creator when no one understands what you're doing, and then people start copying you. Right? That's kind of the model there. So, interesting sort of way of looking at this. But I think that this is understanding how this interacts and how AWS can provide lots of support for you to build on top of that, I think is where I'm going here. Another thing is how do you build this leverage? And I want to talk about, a friend of mine, Simon Wardley, has a whole set of thing about building Wardley maps. So this is kind of the core map. It shows you how things evolve along the bottom. You start with something new, it's unknown, it's uncharted, no one knows how to do it, and eventually it becomes very well known and commoditized, and it becomes the basis for the next generation. So AWS is basically building things that it's driving to the right, and you can build stuff on the top that hasn't been built before and figure out where to do it, and then you basically drive those to commodities and build the next generation. What this means is, and we're rapidly going through these cycles now, it means you can't expect for something to be innovative for a long time. It's going to commoditize. And I think what you're seeing right now with things like AWS Lambda and serverless is it's moved from being a really confusing thing about 3 years ago when we launched it to, okay, we figured out how to use it. And during this year, it's really gone mainstream. We're starting to go mainstream. In 2018, it'll be fully a mainstream service. It's something where everyone will know how to use it. Most people are using it. The tooling's in place. All the things you need, the monitoring tools, everyone kind of ends up supporting it. So I think that's what you're seeing around serverless as it moves through this into, so it's somewhere moving into the middle of this range, whereas it started off on the left. You're starting to see that with machine learning and deep learning. It's kind of in the process of moving from being something brand new that only a few people understand to mainstream use cases and getting easier and easier to use. And what can you build on top of that? What can you do with recognition? It can recognize 100 faces in a crowd for you and figure out where the celebrities are and all those kinds of things. You can build something on top of that you couldn't build before. That's the kind of building on that I'm talking about. But then, when you start leveraging all these capabilities, you're building in dependencies. So I'm going to talk a bit about what I call lock-in and the life cycle of dependencies. And I kind of break this into choosing, using, and losing. And I'm going to use an analogy here, sort of relationship analogies, and I'd like to apologize to anyone in the audience that's going through a bad relationship at the moment. I don't want to push any buttons, but hopefully your enterprise sales reps haven't been around recently. So what's the ROI for each of these phases? You're going to be choosing a technology, and they put some effort into doing that, and what return do you get? You're then going to be using that to get something done, and then so how much effort does that cost? How do you get out of that? And then finally, how do you break up? How do you stop using a technology? How much work is that, and what opportunities does that give? So I'm going to kind of run through these phases. And the real thing here is not just there are all these phases. This is changing, and this has changed as technology and practices have evolved. So it's not the old way. So I'm going to contrast the old and the new, the old world and the new world for each of these. All right. So choosing. We're making investments, like dating, I guess. But what we're doing is we're negotiating, learning, experimenting, hiring experts, building, installing, customizing, developing, training. Well, those are the things you have to put in to do a proof of concept to do this. And one question is, how long do you spend doing that? Does it take a long time? And there's this great Scott McNealy quote, the best decision is the right decision. The next best decision is the wrong decision. And the worst decision is no decision, because it's just like hanging out there, haven't made up your mind yet. But you got to get this right. You don't want to be analysis paralysis, or you don't be a snap judgment. It's like cold feet or the Vegas wedding. I guess we're in the right place. Hopefully no one gets married during reInvent. But right, both of these you want to be somewhere in the middle where you are making a considered opinion, but you're not just going to sit there and not make your mind up forever. So you're going to make this commitment. Now, if you're in a model where you tend to do development and sort of waterfall model, and then you hand it over to operations, that's the point where the lock-in happens. When the development team is dissolved and it becomes an operations problem, you're turning the key in the lock at that point, right? Until that point, while development's on the case, they're still mutating the system. It's not actually locked in yet, but operations lives with this lock-in. And this is actually why operations people hate lock-in and developers don't care so much, because it's like the operations people are the people having to deal with the divorces, right? But they don't get to do the dating part. That doesn't sound like a fair kind of trade-off here, right? So the analogy gets a bit stretched, but hopefully you're getting it. So the old world, this is the really interesting thing. In the old world, we had a monolith, so everything is all in one. If you want to get off this monolith, you have to change all of it. In the new world, it's microservices. It's fine-grained. You can change one piece at a time. And it's a proof of concept install. I used to work on POCs with some microsystems. It takes 6 months to a year just to evaluate whether they should use the technology or not. Now it's a web service. It's open source. It's a free tier. It's a free trial. I don't have to talk to a sales rep to try it out. Instead of months of working on this, it takes minutes. And instead of hundreds of K or millions of dollars just evaluating whether you should use the technology, it's basically nothing to a free tier kind of thing or open source to maybe you spend a few $1,000s trying something out. And that's a radically different place to be in. So the cost of trying something new is much more like just having a friend for a while than getting into a whole should we get engaged, right? So it's a much different level of commitment involved here. So that's the choosing side of it. So let's look at using it, running the family if you like. What's the cost of setup? What's the cost of operation? You have to do capacity planning. You're doing scenario planning. There's incident management. You have to tune it. You have to play with capacity planning, utilization. And then what do you get out of that? Well, obviously the capability of the service. You're doing this for a reason. That you get some availability, functionality, scalability, efficiency, and agility. So that changes again with the old world and the new world. In the old world, it's a frozen installation because your waterfall model, you don't have any developers. You have to start a new project in order to modify your system and to unlock that project and migrate from one database vendor to another one or upgrade from one software package to a new version of it. Nowadays, it's continuous delivery. The development team is continuously mutating a service. They're a product team, not a project team. And that switch from, quite often, this is actually something that the executive in a lot of organizations now are hearing, the move from project to product. And some people have gone all the way and done that transition, and other people are still looking at it. But I think people generally are hearing about that being one of the key transitions as you're moving from the old world to the new world. Instead of ops being a series of specialist silos, it's the developer making API calls. I can configure the network, I can configure the database, I can configure all my other bits and pieces without having to go and file a ticket with the DBA or the network engineer. Capacity upgrades are expensive things you have to plan for in the old world. In the new world, it's elastic. You should be auto-scaling, or maybe you just redeploy on a different sized instance if you need a bit more CPU or memory. Utilization from low to high because you're not wasting capacity, and a very low cost of change over a high cost of change. So this again has moved everything on. All right, so that's the fun part. And then we get to kind of the breakout part. There's a lot of negotiating time. You might have contract penalties. There's replacement costs, a lot of effort to decommission the system. And even when you got rid of it, there's this archiving, sustaining legacy. You haven't actually got rid of it. You've still got stuff. You have archives in the format for that old database or whatever it is. Or, think of sort of spousal support or child support or something, right? If you want to keep the analogy going, right? There's these things. That was a long time ago, but it's still costing me money. That kind of thing. So, what you get out of it is reduced spending, more advanced technology, you've got better servicing, agility, scalability, and you get to do a choose again. You get to go date again, find something new, and play with a new toy. So that's cool. Old world, it was monolithic. It was all or nothing. In the new world, it's a microservice. You can do one microservice at a time. You can refactor that to have a different dependency. If you want to move from MySQL to Postgres for some reason, it only touches one corner of your system. It doesn't touch every part of your system. If you're doing agile continuous delivery, it's pay as you go. You don't have to go, go to court over a contract because you're trying to get out of it. You just stop paying this month, or you stop using it and your bill goes down. And the other thing that's interesting is in the old days of data centers, it's local dependencies. You're on the same network. You have to be right next to this thing because that's the way the protocol works. What we have now is web services. And remember, they're web services, not just services. They are accessed over the web, they're authenticated, and they are remote. So you could actually, and I've heard a few cases where you do this, you can migrate part of your application to a different region or a different provider and leave other parts here. You don't have, it's not an all-in-one thing anymore. In fact, most applications are a mashup from many providers. You might have Twilio there, you might be doing authentication with Twitter or Facebook. Those aren't part of your cloud app. They are web services that you access. So because we're building these systems as web services, we can actually distribute them, and that also means we're much more fine-grained and you can delay. You can move the expensive part of your application to a more efficient system for operating it while leaving everything else alone. You don't have to move everything in one go. So that's giving us a huge amount of flexibility. All right, so old world, monolithic, on-prem, waterfall lock-in, and the new world is agile, cloud-native micro-dependencies, right? So instead of taking years, it takes weeks. It takes sort of millions of dollars to do a migration. You're talking about hundreds of dollars at a time, maybe. Instead of hundreds of dev years, it's a few dev weeks. Instead of talking about lock-in, you're really just refactoring. And instead of dealing with lawyers and contracts, it's really about self-service. So I think the bottom line here is that this ROI for going through this process has really changed a lot. And there are people like, well, I don't want to use, really, this comes out of like, well, should I be using every capability of a cloud vendor? Well, if you can just switch these things in and out, then there's no reason not to use them, right? We're not talking all in one. You're not saying that if I touch any bit of Lambda, I'm locked in for millions of dollars and years. You're locked. You spent 2 days coding this thing. You could spend another 2 days coding it again, right? I don't care about locking in if it's 2 days more work to get unlocked. It's a micro dependency. So because of this, I think that it's all much more incremental. So that's my little rant about dependency and lock-in. So I'm going to talk a bit now about chaos architecture as we wrap up here. So what I've seen is this migration where, to start with, people were using cloud for speed, and then they started to get good at building cloud-native applications that were very elastic. And then they started using some of the advanced features of the cloud, and they've got more interesting higher-level applications that build on top of the cloud. But we're starting to see a new class of applications emerge, which you can think of as very high criticality applications. Think about core banking back-end applications, things that people are seriously shutting data centers that have mainframes with stuff that runs their business on them, and they're going, no, we're moving all this to cloud. How do we do that? All right, and well, if you've got a bunch of COBOL programs that move stuff from one ISAM file to the next, that looks like an S3 bucket and some Lambda functions to me, so that will probably run in the free tier or something. Anyway, and I've got at least one case where a mainframe is replaced by a free tier. Well, it could be. Tell me if you come up with more examples like that. But if you're jumping 4 or 5 generations of technology, you can get some just like radical improvements in efficiency. That's kind of the point I'm making. But what we're finding is some of these applications really are critical. Is like if this goes down, billions of people don't get paid, or the GDP of a country gets affected, or somebody gets stuck in an elevator, or cars crash, or bad things happen in the world. And we want to make sure that we're coming up with architectures that are extremely resilient. And one of the things that we did, back, whatever it was, 7 or 8 years ago at Netflix, was we actually were trying to build TV sets that worked like TV sets instead of things that were somehow connected to the internet, and you had to apologize for them not working occasionally, right? Because it's hard to explain to a 7-year-old why they can't watch that cartoon. And the Netflix's cost of this going wrong is largely brand reputation, but that is still a very large cost. So it was worth optimizing for this. But we're now getting into things where people could die, or large amounts of money could get lost. So, and it's not that this hasn't been happening, but we're thinking about the architecture for this. So I'm going to spend the rest of the time talking about what does this architecture look like? And I'm breaking it into 4 layers, 2 teams, and an attitude. So I'm going to lead you through what I mean by that. So here's the first layer. We have all these infrastructure, all these services, whether it's on-premise or a cloud vendor, you can distribute all these things. And we want no single point of failure. We want to make sure that everything we do, there are 2 ways to do it, there are 2 places to go to get that data or get that process. That's the fundamental principle of getting some high availability. If you've got any single point of failure in your system, then you have a vulnerability, and you have to figure out what's the probability of that happening and what's the likelihood, how are you going to deal with it. So that's the first level, getting no single point of failure. And the interesting thing here is we want no single point. That means we need to be distributed, right? No single point. So we're looking at being distributed. And we don't want to have any no single failure, so we need to be replicated, right? So we need to be in more than one place. We need to have more than one way of doing a thing. And this sort of distributed, replicated thing. And then on top of that, we want to be automated because humans get stuff wrong, and automating things will make it more reliable if you get that right. And cloud is really the kind of the name we give to this distributed, replicated, automated principle. And that is what cloud is. It's all these levels of automation that let you build these systems. So I think we have a really interesting opportunity to build vastly better systems than we've had before because we have all of this automation that we can build reliably on it. So that's the infrastructure layer. And there's a lot of patterns emerging there. If you look at the well-architected guide that AWS produces, there's a whole section in there on well-architected patterns for building sort of good distributed, highly available architectures. The next level is the switching and interconnecting level. Because if you've got 2 places to do something, you've got to figure out how did the data, 2 places to store data, how did the data get to 2 places, and how do you keep it in sync? So you've got to have an architecture that solves for that problem. So data replication. You've got to route traffic between places. You've got to route customers to the traffic, to the right location. And if something goes wrong with some location, you have to reroute customers somewhere else. Like, how do you automate that process and do it reliably? And then once it's got better again, how do you route it back? Right. For your customer, let's do some audience questions here. How many people here have a backup data center in their infrastructure? How many of you fail over to it regularly? Okay, probably a few people looking a bit embarrassed here. If you went to the CEO, and if the CEO is talking to the CIO, and the CEO says, you got a backup data center, right? The CEO says, oh yeah, we've got a backup data center. And this says, so how often do you fail over to it, and when did you last do it? And if you get the embarrassed silence, that's kind of a bad position to be in. There are certainly some customers I've talked to who do regular failovers, and they're doing this very reliably. And there are others going, no, it's like availability theater. It's like taking your shoes off to go through an airport. You have the appearance of availability. In practice, it's not going to give you any real benefit. I mean, when you get an outage, you will spend several days trying to get everything back up and running. And then if you try and fail back, it'll probably take a couple of months to figure out what state it's in so you can come back without causing another outage. So that's a big mess. So the problem here is that if you don't test it, you don't know what you're doing. You don't know how good it is. But the real problem here is that the code that's involved in dealing with these kinds of failures are the least well-tested code in your system, because you don't exercise it. The codes and the practices and the user experience of how you deal with it, if that is the least well-tested code, it's the code you want to work most when you're in the middle of an outage, is the thing that is actually least likely to work. So you quite often see failures where a small outage caused a slightly bigger outage because something wasn't configured right, and then the system attempted to do some kind of response to it, which caused an even bigger outage. And then everything sort of collapses in a big heap for a while. That's a bit too common of a scenario. All right, the backup data center. What's the best description of your backup data center? Availability theater, infrequent partial testing, maybe regular tests during maintenance, or frequent failovers during production to prove no one can tell it's happening, right? And there are people doing the last one. And again, I left Netflix 4 years ago, but that's kind of where Netflix is now. They are doing data center level, well, they're doing region level evacuations about every 2 weeks, and it takes them 6 minutes. They don't even call a meeting or they file a ticket saying it's happening, but they don't like email everyone in engineering, oh my God, we're going to do another one of these. 4 years ago, that was oh yeah, we're going to do this, get everyone in a room, and we scheduled it in advance, and we did it once a quarter, and they've got better and better at this, so they do it every 2 weeks. And this is one of the principles of continuous delivery, is if it hurts, do it more often, because then you will automate away the pain until it no longer hurts, and it's sort of that principle applied here. So, what are you trying to do here? You're going to route updates and customer requests to specific regions and services. You've got to figure out how do you do that routing, how do you switch it, how do you replicate data and reroute those? What's the architecture there? And your switching mechanism must be more reliable than the things it's switching between. This is one of the principles of redundant systems. If you've got to switch between two things, the switch has to be more reliable than the things you're switching between. Otherwise, your system is less reliable than just using one thing, because your switch will fail and it will take out both of your things more often than the actual underlying thing will fail, right? If anyone that's done any reliability engineering, that is one of those principles that they teach you. All right, so we've got to apply that. So that's the switching layer, and I think it's one of the most poorly tested systems, and we need to get better at doing that. All right, the next level up, applications. What happens to an application if it sees an error or gets a slow response or the network drops? Does it fall over? Does it go 100% CPU busy? Does it write the wrong data into the wrong place? All kinds of bad things happen if you don't test for this. This is really difficult if you built a monolith, because your monolith does 100 different things, and it's got all these different states it's in, and it's very hard to reason about, is it behaving correctly when you remove or mess with one of its inputs. If you've got a microservice that just does one thing, it's only got one way of asking it to do one thing, and it has a bunch of dependencies. It's much easier to manage the availability of those. You can say, okay, if it gets one input wrong, what happens to the input? What do you want to do? Sometimes you get into these interesting discussions where people say, so what do you want the application to do when this piece breaks? And it says, no, I don't want it to break. No, but what do you want it to do when it breaks? And they won't answer the question. You have to just keep beating on them. No, it's got to do something when it breaks. Now, we can stop the whole world. No, we don't want to do that. Okay, so in that case, it has to keep going in some reduced capability state, and what do you want that state to look like to the end users, and can you come up with something? And if you can sort of battle your product managers into that frame of mind, which takes a while, you can actually start building a system which has a series of degraded responses to failure and is much more reasonable. There's this idea about permissive failure. Like, if you can't figure out what to do, should you just stop and throw an error, or should you return something that seems vaguely reasonable that you might want to get away with? And one example of this is if you try to log into a system and the login system isn't there, like the subscriber service is down, but you still have a cookie from last time you logged in, but it's invalid. You can't even test whether it's a valid cookie anymore because it's maybe timed out. Should you let that user do something? Right? Well, if you're streaming a movie, you said, yeah, you look like you were a customer once. I'll just show them a movie, right? Because it's our fault that the subscriber service is down. You should just do permissive failure and just let this happen, because you can't tell whether it's our fault that we can't tell whether we should let you do this or not. And the consequence is basically a very low cost to us, right? So what's the consequence of letting somebody do something? The other consequence is you just have a big error message on your TV set. That's a worse consequence than maybe letting somebody watch a movie for free because they're a subscriber that just expired. And you kind of think about this in that way. So there's a lot of careful design, but this is where the application layer gets more interesting. Okay, so these microservices, like I said, they limit the blast radius for anything going on in your software. So you can use circuit breakers to limit the damage, bulkheads to prevent it from spreading. There's this pattern called ditto, do idempotent things to others. And there's a talk from QCon London from Starling Bank where they described an architecture, and they came up with a really, really long acronym for it, and somewhere in the middle was ditto. And that was the sort of the core thing. So you want to have a lot of the patterns here, things like event sourcing and CQRS, so those of you in the sort of application development space, those are the kinds of things that people are doing. And a lot of append-only logs. You want to avoid anything to do with update and delete. Like you delete something by writing a thing on top. It's called tombstones, right? You write a tombstone on top of the old thing, you just append to the log, and you just look at the log and say, well, there's a tombstone, so this thing shouldn't be there anymore, but I'm remembering that the old value is still there, so you can wind things back. So everything's built as immutable append logs. And this is the kind of new patterns that we're seeing in, well, they're not new patterns. They actually go back 4,000 years to Babylonian clay tablets when you had to double-entry bookkeeping was invented. But we're reinventing some of these things. Okay, so that's the application. Let's just wrap up a bit by looking at the next layer. This is people. So what do people do when something goes wrong? Typically, they make it worse. We've seen this. This is not that much of a joke when you realize that the Chernobyl nuclear power meltdown was caused during a test where they were testing something. Then they got confused by the results of the test, and then everything escalated to the point where the actual meltdown happened, right? So there are the software equivalents of that around. But if you built a really, really wonderful system that totally could deal with anything that could go wrong, and something goes wrong and it's dealing with it, quite often the operators will get confused because now it's behaving differently, and if there's a knob they can turn, they'll turn it the wrong way. And if there's a button that says do not push this button, they'll keep pushing that button, and they will break it. And we saw that many times at Netflix. I've seen it lots of other places. It's just a thing that happens. So how do we deal with this? Well, you have to train people, right? So let's look at a little analogy. So everyone here at some point in their life has gone through a fire drill, right? You work in an office. At some point they say we're going to set off the fire alarm, and you're going to walk down the stairs and stand in the parking lot. We'll do a roll call. Okay? Pretty much everyone in the world has done that. It's universal, right? This isn't just something that we did once. It's a really universal thing. But the cool thing is that when buildings are actually on fire, this saves people's lives. And the first time I gave this talk was just after the earthquake in Mexico. There was a big earthquake in Mexico City. And that 2 hours before the earthquake, there was a public earthquake preparedness drill, like in the whole city, right? They set off the alarms. This is what to do. This is where you go. Everyone practiced it. And 2 hours later, the earth starts moving side to side several feet. Okay, this isn't a drill, right? You know this is the real thing. And I'm sure that saved lives, right? So how do we do this? So the problem is, who's running the fire drill for IT, right? We don't go through these training exercises. And this is where this sort of idea of chaos engineering comes up, and there's probably some other talks this week from the Netflix folk about this. And actually you'll see Nora Jones is one of the authors here in Werner's keynote on Thursday morning. This is a great book. It's a free download. They want your email address, but Ro Riley probably already have your email address. So it's one of those. They wrote this book, and it's got all the principles in it. It's a lot of good stuff in here. And I'm just going to give you a very high-level view of what's going on here. So it's tools for managing, for basically proving that all of these layers are working properly. And you do, at the people level, it's game days, it's exercise. If you've never been on an outage incident, conference call, you don't know how to behave. Like it's a training thing. You should practice these incident calls, because there's a way of behaving that's very efficient at managing the response to an outage. And if you don't practice that, you will just spiral out of control. You'll you'll turn something that should have been minutes into hours. The Simian Army open sourced that. There's a bunch of other tools. There's chaostoolkit.org as an attempt to build an open source project around that. Those of you that know Russ Miles, he's running around in Europe doing all talks on chaos engineering, and he's been creating this chaos toolkit. Netflix have a thing called CHAP, which is the chaos automation platform, that they run thousands of automated experiments a day by introducing errors into their applications across the critical path in production to prove that the system still works. When you do that. Then Gremlin is an ex-Amazon, ex-Netflix engineer who's founded a company to do this automatically and to do things like tracking the exact state you're in, so that when things break, if something goes wrong, you can back it out really quickly. You want to be watching a business metric, and if anything you're doing to introduce chaos affects the business metric, you want to unwind everything back to zero again. All right, so I'm down to my last minute here. So let's look at the other side of this. On the security side, we've actually learned how to do this too, because the security of your system is only as good as its ability to withstand break-ins. And a lot of companies now have a red team, and that team's job is to break into your system, and your regular securities team is to prevent that happening. And then they are basically, the only way you know your regular security team is doing a good job is if the red team can't get in. And similarly, your SRE team, or whatever you want to call it, that's trying to keep your system running, has the chaos engineering team making sure they're doing a good job and finding the weaknesses. So those are very similar. This is the two teams. And then the attitude is you're breaking it to make it better. So I just have a couple more slides and then we can wrap up. So the risk tolerance. Who really is at risk for what? Is downtime a bigger risk than consistency? So there's this whole idea, do you want consistency or do you want availability? And those of you who know the CAP theorem, this is kind of why it bites you. You have to figure out what to do. If it's okay to be down because you need to be consistent, that's fine. But quite often people pick consistency when they really, really needed availability and they just hope they're going to get away with it. And then you have this incident life cycle where you need to mitigate, restore, and adapt. And the loop back here is really an anti-fragile loop. There's a book by Nicholas Taleb, Anti-Fragile, many of you may have seen it, which is about you exercise things in order to make them stronger, but not so much that you break them. What we're really trying to do here is break it to make it safer. And there's this new view of safety. This is actually in the whole safety critical industry. There's a podcast, the Pre-Accident podcast by Todd Conklin's worth listening to. I actually did a podcast with him on Chaos Monkey years ago. John Allspaw, stellar.report is a URL, that .report. And Sidney Dekker, there's a book called Drift into Failure, which is a really good introduction to these concepts. So don't read it on the plane on the way home. There's a lot of plane crashes in it. So what we're really doing here, that failures are this system problem, and its lack of safety margin. We're trying to manage the margin. And think about if you're blindfolded on a cliff edge, you're going to test the ground to make sure you've got ground to walk on, to be really careful. And what we're really trying to do here is hypothesis testing to make sure we really have the margin we think we have. And that's the whole principle behind this chaos engineering. All right. How do you pick a test? The lineage-driven fault injection, something there's a QCon London talk from last year about this. And you build dependency graphs and track those in. So I can finally get to the end. So what you really want here is experienced staff. You want robust applications. You want a dependable switching fabric, and then a redundant service foundation. You put all those together, you can build 4 nines, 5 nines, invincible, like totally resilient system. But getting all these lined up is quite a lot of work, right? So that's basically it on that, and these were the different things I was talking about, and I'll be around for the rest of the event, so you can find me, and I'll hang around a bit outside afterwards to chat to people, so I think I'm way out of time here. So thank you.